we're not worried about it. We're worried about getting started with calculus. First lecture. Okay, quick bookkeeping stuff. So I sent you the syllabus and the book in your email. I think you should have also already gotten it.
Yes.
You know?
Yeah, I saw that.
You were just added, so make sure I get you the materials.
Okay.
Okay, before you leave today. So that's book, that's syllabus. If you have any questions about that, always feel free to reach out. You can always email me or you can text me. I prefer you text me. Then I'll immediately respond. An email, very easy to miss. In case you don't know me, my name's Donald Timpson. My education, I jumped around a lot in college. I started out majoring in healthcare, then I switched to finance, then I switched to engineering, then I switched to computer science, ended up double majoring in math and computer science. Professionally, I work as a software engineer for a company called Align. I create iOS apps. That's what I do professionally for a living, and obviously volunteer teacher here on the side. So that's, since one of my majors is math, pretty good fit for me. So is there any other bookkeeping stuff that we need to do? Did I not start the camera?
No, you uploaded it.
Oh, YouTube, thank you. So I keep a YouTube page. You can just search my name, Donald Timpson. There'll be a picture of me where I upload all my videos. On the home page, when you go to it, there's first gonna be like a list of recommended videos for you. Second is gonna be creative playlist. Third, it's gonna say school year 2024 to 2025. And that grouping will be the playlist for this class. You could also probably try and search it directly, but we'll say calculus 2024. That's where all the lectures will be. Usually I'm able to upload those the same day that they're recorded. So this will be up before the end of today, most likely. Any other bookkeeping stuff? Okay, so this first lecture is going to be completely supplementary. We are not starting on the book today. We will start on the book next week. I'm going to give you my own, what I think should be your foundations of trig, and then some other stuff that I like to cover a bit more thoroughly than this author is going to do. And then we're just going to do exactly what the author does. After that, we're just going to follow the book. It's a pretty mainstream book, a pretty standard Calculus 1 course. If you were to go take it at university, this is pretty much what the course would be. So outside of that, we're pretty much just following the textbook. So first lecture, just supplementary. We will touch on everything that we talk about in this lecture for the most part, again, later in the book, as the author reviews it. So I want to give my review, then we'll let the author review. That makes sense? Mm-hmm. So with that, we'll start my review. So first, we got to quickly lay our trigonometric foundations for calculus. So we're going to go back to some basic geometry, and we're going to start with a quick proof. That the angle sum of any triangle is 180 degrees. That's the first proof that we're going to do here today. You understand what we're saying? If you add up that angle, and that angle, every single time it will come out to exactly 180 degrees.
Yep.
Okay, so how does the proof start? First, I construct this red line through the base of the triangle. Doesn't matter which side you choose. Now pick the point opposite that side and construct another parallel line. So this line's parallel to this line. With me? All right. Now, extend the line of the triangle. Extend this line. And extend this line. You with me? How does this angle compare to this angle?
They're the same.
They're the same. They're what we call vertical angles. So they're congruent to each other. Perfect. How does this angle compare to this angle?
It's the same.
They're also going to be the same. Those are called corresponding angles if you remember back to your geometry. And then finally, should do 2 lines for that. That's the same as that. And then finally, how does this angle compare with this angle?
They are also the same.
They're also the same. Those are vertical angles. When a line intersects 2 parallel lines, it intersects them at the same angle. Vertical angles. So, what is this angle plus this angle plus this angle?
It's a straight line.
A straight angle, or 180 degrees. And so that's congruent to this angle plus this angle plus this angle. So the angle sum of any triangle, 180 degrees. Okay, got a little bit of our foundations. The real foundation we need is Pythagorean theorem. It's the most basic foundation we need. Okay, so we're going to prove the Pythagorean theorem. What is the Pythagorean theorem? The Pythagorean theorem is, if you give me a right triangle, so this is a right angle right there, with side lengths A, B, and hypotenuse C, then A squared plus B squared equals C squared. So we're showing that A squared plus B squared equals C squared. So here's our triangle that we're talking about. Now, first thing I'm going to do is I'm going to construct these 2 squares. I wanted to draw them kind of nice so I did it ahead of time. these two squares, notice, what is the length of this side of the square?
AB.
And what's the length of this side of this square?
AB.
So what is the area of this whole square?
AB squared.
A plus b squared. That's what we mean by squaring a number. It gives you the area of a square with that as its side length. So the area of this square is a plus b squared. And the area of this square is
A plus B squared.
a plus b squared. Right? Okay, so these two outer squares have to have the exact same area. Now let's do a little bit more fine-tune. I brought a small marker, I think. But let's break down and look at each of these areas now. So look at this little square right here. What's its area?
A squared.
A squared. It's a times a. So this little square has area a squared. What's the area of a rectangle?
Length times width.
Length times width. Or in this case, this rectangle's area is
AB.
a times b. And this rectangle's area is
A times B.
a times b. And then finally, this big square, what's its area?
B squared.
B squared. Or b times b. So, this bottom one was for this right-hand square. This one, its area is also equal to a squared plus 2ab plus b squared. You might be thinking, why don't we just apply the algebra to that? That's using algebra. We're doing this geometrically. This is how you might come up with an algebraic proof for that a geometric proof for that algebraic rule. Okay, now let's focus on this square for a second. Look at one of these triangles. Actually, before we look at the area of one of those triangles, let's make some more observations. So, first off, I made a square using our initial triangle with one of its sides. So I know that's a right angle. I know this bottom angle down here is a right angle. I know this is a right angle. I know this is a right angle. With me so far?
Yeah.
Now, you might remember your congruence theorem, side, angle, side. So this triangle is congruent to this triangle, is congruent to this triangle, is congruent to this triangle. Because they have two sides the same length and an angle the same. So that means this side length, this hypotenuse is C, this hypotenuse is C, this hypotenuse is C. So those are all the same triangle. With me so far?
Yes.
Okay. Now, I need to argue that, I want to argue that this angle right here, maybe I'll do it in red. I want to argue that this angle right here is a right angle. Because I want to argue that this inner red figure here is a square. And then I know how to talk about its area is going to be c squared. So that's the argument that remains to be made. Now, what is the angle sum of any triangle?
180 degrees.
180 degrees. So I'm going to call this small angle up here, we'll label that with an alpha, sorry, small alpha, and we'll call the bigger angle beta. You with me? And our red angle x that we don't, our red angle that we don't know yet, we're trying to prove it's right angle, we'll just call that x for now. We're not sure what it is. Now, this triangle is congruent to this triangle. So this angle down here, what's this angle?
Alpha.
Alpha. And what's this angle up here?
Beta.
Beta. Okay. Now notice that alpha plus x plus beta is what?
180.
180. So I know alpha plus beta plus x is equal to 180. But I also know from the interior of the triangle that alpha plus beta plus 90 degrees is what?
180.
180. So I also know that alpha plus beta plus 90 degrees is equal to 180. Right? And so what does my x have to be?
90.
You can do some quick algebra to prove, okay, so that x has to be 90. The same thinking goes for showing that that's a 90 degree angle, for that's a 90 degree angle, and for that's a 90 degree angle. So we're guaranteed that the internal figure is in fact a square. Yay. So what's the area of this internal square?
C squared.
C times C, C squared. Now finally, what is the area of one of these triangles? Remember the formula for a triangle?
A times B times 1/2.
Half the base times the height is a mnemonic we use, but
Right. 1/2. Yeah.
what you're saying is fine.
1/2.
Half the base times the height, or it's 1/2 times A times B. 1/2 A, B. And that's the same for all 4 triangles, right? So, calculating the area of our top of our left square, that's what this line was, that is going to be equal to, let's see, I have 1/2 AB, 1/2 AB, 1/2 AB, 1/2 AB. I have that 4 times. So I have 4 times 1/2 AB plus C squared. With me?
Yep.
So, don't have an eraser. So, using that, I know that this is equal to this. So writing my top one first, well, I'll write my bottom one first. I know that a squared plus 2ab plus b squared is equal to 4 times 1/2 is 2ab plus c squared. Subtract 2ab from both sides, and what am I left with?
A squared plus B squared plus C squared.
And there it is, your Pythagorean theorem. Any questions so far? Okay, so that's our quick geometry foundations. Now we're going to jump into trig. There's 4 basic definitions you need to understand trig. Those are the definition of a radian, the definition of pi, the definition of sine, the definition of cosine. You get those 4 things, you pretty much have your foundations for trig. So we're going to start with the first one. We got some circle here. Here's a circle. Its circumference, we'll say, is c. What circumference?
It's the length of the circle all the way around.
Yeah, the perimeter of the circle you can think about as. So c is a perimeter, the distance all the way around the circle. D is a diameter, that's the distance from going from one side of the circle to the other, as long as you go through the middle.
Yep.
And then the radius is just half the diameter. Okay, what is the definition of pi?
Circumference divided by the diameter.
Is that right?
I don't know.
Isn't it 3.14159 blah 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 blah?
That's the approximation of
No, that's just a numeric approximation for the ratio. The definition of pi is circumference over diameter. That's its precise definition. It happens to be the case that when you plug in any circumference and diameter you want of a circle, it comes out to roughly 3.14159 da 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 da.
The same for every.
Yes, it turns out whether it's a small circle or a big circle. The bigger your circle, the bigger your circumference and diameter.
Yeah, that's true.
If you double your circumference, you double your diameter. Gives you the same number.
Yeah.
Okay, now from this equation, multiply both sides by d, and I get that circumference is equal to d times pi. You see that?
Yeah.
Finally, diameter is the same thing as 2 radiuses. So I also get that c is equal to 2 pi r. I'm going to put the r at the end. So 2r pi or 2 pi r. You good there? Okay. Did I lose anyone? Okay. So here is our distance around the circle in terms of our radius. Question. If I have a circle whose radius is 2 meters, what's its circumference?
4 pi r, or
4 pi meters, whatever that comes out to. Right?
Yeah.
So, a little over 12 meters. Okay. So that's circumference. Now, what is the definition of a radian? First off, let's think about the definition of an angle. What's the definition of an angle? It's 1/360th of the circle.
That,
Completely arbitrary.
isn't that degree?
That's 1 degree. Oh, what did I say?
You said angle.
Sorry. What's 1 degree?
It's 1 degree. 60.
Why on earth do we divide a circle up into 360ths? What an arbitrary thing to do. It's a good number for arithmetic if we're worried about having to do division by hand,
Yeah.
which is why it was introduced. The more advanced maths, that's not so much a problem. So, we're going to introduce a new way of measuring angles. This new way of measuring angles is called a radian. So imagine that you're on this circle right here. You start right here. And you walk 1 radius around the circle. The angle that you would have walked, this angle here then, is 1 radian. A radian is the angle you walk going 1 radius. Question. If I walk walk all the way around the circle, how many radiuses have I walked?
2 pi r.
No, 2 pi radiuses.
Pi radiuses.
This is walking 1 radius. This is walking 2 radiuses. This is walking 3. If I walk exactly halfway around the circle, I've walked exactly pi radiuses.
Yeah.
Walking 4 radiuses, 5, 6, and then if I've walked 6.28, whatever it is, if I've walked 2 pi radiuses, that gets me all the way around the circle.
Yeah.
So a radian is the angle marked out by 1 radius,
Radian.
called radian. Why do we love radians so much?
Simplify.
It makes it easy to go from talking about angles to talking about distances. Let me give you an example. I tell you Jack is standing on a circle. He walks 135 degrees around that circle. The circle has a radius of 10 meters. How far did he walk? So we've got our circle has a radius of 10 meters. We know he walked 135 degrees around the circle. How far did he walk?
Something 2 radians.
You're struggling. Point is, you can't easily just do it in your head like that.
Yeah.
Now let me replace this and say he walked 3/4 pi radians around the circle. If he walked that many radians around the circle, then he walked that many radiuses around the circle. So he walked 3/4 pi radiuses around the circle. Or in other words, it's equal to 30/4 pi. Or you can simplify it.
Yeah.
But the point is you can calculate the answer like that. That's why we love it. If you gave me the distance, I can quickly tell you the angle if I know the radius. Just divide by the radius. If you give me the angle, I can quickly tell you the distance. Just multiply by the radius. And so it makes going back and forth between talking about distances and angles very simple. That's why radians are used. That's the beauty of it. Okay, so radians, let's do some quick conversions. Each of you are going to tell me one. We'll start here, we'll go down, then to you, and restart. 360 degrees, how many radians is that?
That's 1 full circle. So that's 2 pi radians.
2 pi radians. Perfect. Next, what's 90 degrees?
0.5 radian.
0.5 radians, or 0.5 pi is what you meant to say. Or in other words, we say pi halves.
Pi
Okay.
halves. What's house from?
Huh?
Pi halves.
He's saying
1/2 pi.
pi over 2 is the same thing as 1/2 pi. It is the same thing as 0.5 times pi.
Yeah. What did you say? You said house?
Pi halves.
Pi halves. Pi over 2.
House.
Pi
Halves.
halves.
Oh.
As in we're halving pi.
Okay.
I should enunciate better. Okay, so pi halves. That makes sense?
Yeah.
Okay, the next one, 180 degrees.
Pi.
Is just pi. All right, 270 degrees.
3 pi
3 pi,
radians.
not quite 3 pi. Let's think about it. How much, pi gets me halfway around the circle.
Yeah.
So pi gets me here, 2 pi gets me here, 3 pi gets me here. We're trying to get to the bottom of the circle. 270 degrees,
So
bottom of the circle.
2.5 then, or 3.5.
You're saying half that. Pi halves, pi, 3 pi halves.
3/4 pi then.
3/4 a circle.
Yeah.
So what's 3/4? What's 3/4 of the circle?
3/4 of the circle is 270. Well,
No, just calculating it. 3/4, 2 pi gives us the whole circle, right?
yes.
And you're calculating 3/4 of that.
Yes.
So you just have to do, what's 3/4 times 2?
3/4 times 2 is 6. Yeah, 6.
6/8, which reduces to. You can think about the 2 in the bottom and top and bottom cancel out.
Yeah.
And you're left with 3/2 pi. Or in other words, 3 pi over 2.
Yeah. So, yeah.
So that's your answer. You see it? All right, let's try another one. 60 degrees. What portion of the circle is 60 degrees?
That
1/6.
4.
It's 1/6 of the circle. 60 degrees is 1/6. What's 1/6 of 2 pi?
1/3.
2 12s.
1/3 pi,
Oh.
isn't it?
So it's just pi over 3. Yes, you're correct.
Yeah, that's really simple.
Yeah, it's simple. It's just a new way of thinking about it, and it's going to be annoying to think about that way until you get used to it. And then you're never going to go back to degrees, because who would ever use 1/360th of a circle? So arbitrary.
So then 2
Alright.
pi over 3.
2 pi over 3, because there's just two 60 degrees. So 2 pi over 3. Perfect. So that's converting from degrees to radians. That's the definition of a radian. All right, so we covered 2 of our most basic definitions of trig, pi and radian. Now we're going to move on to sine and cosine and their definition. So up here, I have drawn what is called a unit circle. A unit circle is a circle whose radius is a single unit. How are we doing?
Good. How are you?
Lovely. What can we do for you?
Are you missing anyone?
There's a bunch of people in my grade book who are not here, but I don't think they're supposed to be in this class. I think they're in other classes.
Do you want to just give them to me?
So they probably remember. One of them was Kendrick,
Sabrina and
Okay.
Levi, whoever that is.
Levi someone, probably a Hammond.
Levi in your grade.
There is a Levi in my grade, but I know this is.
He's the Baker's last.
Levi Jarris Hammond.
Oh,
Oh,
Jared.
Jairus.
Oh, Jairus.
Oh.
Okay. I have not seen him, but I've seen the other 2. They are probably in other classes.
Okay,
Are they
Okay,
supposed to be
thank you.
here then?
I'll let other people worry about that. My teacher shows up. Okay, so now we move on to definition of sine and cosine. So what I've drawn here is a unit circle. What's the radius of the circle?
1,
1. That's what we mean by unit circle. What's its diameter?
2,
What's its circumference?
2 pi.
2 pi. What's the circumference of a circle? 2 pi times its radius. Quick, 2 pi times 1.
2 pi.
2 pi. There's a quick math. Okay, so by definition, pick any point on the unit circle you want. Any point you want. That point will have an x coordinate. We're imagining this, centered at the xy plane. So this is the origin, 0, 0. Let's just mark some points really quick. What's the coordinates of this point?
1, 0.
1, 0. What's the coordinates of this point?
0, 1.
0, 1. What's the coordinates of this point?
-1, 0.
-1, 0. And then finally, what's coordinates of this point?
0,
0,
-0, -1. Good. Okay, so we're on the coordinate system. So we can talk about coordinates of points. Pick any point on that circle. It's going to have an x coordinate and a y coordinate. Right? X is how far over it is, y is how far up it is. By definition. So, to pick our point, we're going to start by picking an angle. You give me any angle you want. I draw the line out at that angle, and it gives me a point on the circle.
Yeah.
So here you are. You give me the angle. What should we say that is? 60 degrees-ish.
Okay.
You give me 60 degrees. I draw the line out at 60 degrees, and it hits a point on the circle. The x-coordinate of that point, by definition, is cosine of theta. The y-coordinate of that point is, by definition, sine of theta.
Oh.
Really quick, what is cosine of 0 degrees? What is the x-coordinate at 0 degrees?
0.
0.
What is the x-coordinate at 0 degrees?
1, sorry.
1. So cosine of 0 is 1.
Okay.
Yeah.
Good? Let's try another one. What's sine of pi halves? What's sine of 90 degrees?
1.
1.
1. What's cosine of 3 pi halves?
-1.
What's cosine of 3 pi halves?
0.
0. Cosine is x-coordinate. Sine is y-coordinate.
Oh.
There's 2 things up there. All right. Once again, we'll go through having you each answer as we fill this up. All right. So whoever's first, cosine of 180 degrees.
-1.
-1. Good. Cosine of pi halves.
0.
Cosine of pi halves, let's see, pi halves, that's the same thing as 90 degrees, x coordinate 90 degrees, 0, yes. Cosine at 2 pi.
1.
1, that's cosine going all the way around the circle. And now you're stuck with the trick question. Cosine at 84 pi.
Wouldn't that be 1?
That would still be 1. We start here. 2 pi gets us to there. 4 pi gets us back to there. 6 pi gets us back to there. Any even number of pi's, we end up there.
Yeah, that.
So the cosine of 10,000 pi is 1. The cosine of 10,001 pi
That's super. Well, that would be.
is odd, and all the odd ones end up here. So it'd be negative.
Oh, yeah.
Okay. And then back to you. Cosine of pi thirds.
Pi thirds is 60 degrees.
And you shouldn't yet know how to calculate that.
Okay.
So we need to figure out how to do this. The point is, we don't magically know how to calculate the cosine for any of these angles. And in general, if you got a student hot out of trig and you grabbed them and told them that they couldn't use their calculator, and you said, really quick, what's the cosine of 52 degrees? They'd be at a loss. They don't know how to just do that. And that's expected. So you only learn these values for very specific angles. Throughout this class, you can use calculators on your homework, and on some of your homework, you're going to have to use calculators. But when it comes to your test, you won't be allowed to use calculators. And the reason being is I will only pick special angles that you should be able to do in your head.
Okay.
So I would never give you a 52 degrees. I would give you a 90 degrees. Now I'll also give you a 30, a 60, and a 45, and we'll get comfortable with that here in a sec. So you will learn how to do this one. This one, no, you're not going to learn how to do that.
What's the point of cos and sin, though?
Cosine and sine,
Yeah, there. Sine, yeah.
they tell us how to, from an angle, get a coordinate. Which is useful information.
Oh, yeah, that's right. But
Oh.
it changes, though.
It changes based on the angle, but the point is, any angle, I can quickly give you the coordinates.
Just on the unit circle though, right?
Just on the unit circle. We'll scale this up as we go. And we'll tell you how to work with any circle, and then we'll find out the circle doesn't even matter, and we can just look at the triangle. We're using the circle as a crutch for a triangle. Because what we're really talking about is, we're saying, given this triangle, what's this distance, and what's this distance? And those happen to correspond to the x and y coordinates.
But you could figure that out with the given information.
Yes, this distance right here is cosine of theta. This distance right here is sine of theta. Because by definition, what's your x coordinate? It's how far over we go.
Yeah.
So x is cosine of theta. So this distance is cosine of theta. And this height is sine of theta. So we use these trig functions to get lengths on triangles. Trigonometry, it's an analysis of triangles. That's what the tri in trigonometry stands for. Okay. Moving forward, whoever we're on. Sine of 270 degrees.
One or negative one?
Negative 1. Good. 270 degrees right is down here. And the y coordinate is negative 1. Next, sine of pi halves.
0.
Sine of pi halves, that's the y coordinate at pi halves, 90 degrees.
Oh, 1.
1. You get the trick one again. Sine at 19 pi.
Wouldn't that be 0?
0. Sine at 20 pi.
0.
Still 0. Because when it's a whole number of pi's, it either ends here or here. Those 2 points,
Are both 0.
y is both 0 at those points. And then finally, whoever we're on, sine of 3 pi fourths.
I have no clue.
Right. And you shouldn't have a clue. That's good. We'll figure out how to do that one here in a second. Okay? Okay, so there's some practice with that. Now that was on that unit circle. So I know that if my radius here is 1, then x is equal to, if the hypotenuse of this triangle is 1, and this angle is theta, what is x?
Cosine of theta.
It's cosine of theta. This triangle is that triangle.
Oh.
Its x distance is just cosine of theta. I should specify. Cosine and sine, these are functions. You give cosine an angle and it spits out the x-coordinate. Sine, you give it an angle and it spits out the y-coordinate. So you have to put parentheses. We are really lazy. And I'm going to write cosine of theta like that without parentheses all the time. That is because I'm lazy. That's not because that's good. Okay? So, should be cosine of theta. It's a function. And what is y equal to?
The sine of theta.
Sine of theta. Now imagine I took this triangle now, and I stretched it so that the hypotenuse was twice as long. We kept the angle the same, I just stretched it. Scaled it up by a factor of 2. How much bigger did we make the base? Twice as big. And how much bigger did we make the height? Twice as big. So in that case, if this was 2, then that would be 2, and that would be 2. Similarly, rather than stretching it out, imagine I squished it down so that the hypotenuse was now 1/2 of what it was before.
Then it's all 1/2.
That's all 1/2.
Yep.
And in general, if I rescale my triangle so that its hypotenuse is r, then what is x?
R times x.
R times cosine theta.
Or yeah, sorry.
And y is equal to r times sine of theta. And those are the general formulas you use. This is a special case when your radius is 1.
Right.
Here it is in general, for any radius for any r. And we don't even have to say radius anymore, because we don't care about the circle, we just care about the triangle that was in the circle.
And that's just the hypotenuse of the triangle. Just
And it's the hypotenuse of your triangle. Given the once you know the hypotenuse and the angle, the base angle, you can now calculate the width and height of the triangle, or whatever you want to call them. Okay, so now look at this, and imagine that we solve for cosine.
Okay.
How do I get cosine by itself?
You have
You need to do substituting.
You divide both sides by r. If I know that 2x is equal to 10, how do I get x by itself? You divide both sides by 2. The same exact principle, just fancier symbols. I got r times cosine on this side. How do I get cosine by itself? Divide by r. So I have to do that to both sides. So then cosine is equal to what?
x over r.
X over r. So cosine is in general, can be written as x over r if you want x by itself. Or if you want cosine by itself. Where x is the base of the triangle, and r is the hypotenuse.
Okay.
Similarly, what is sine?
It's y over.
It's y over r.
That makes sense.
All right. Now, by definition, let me grab my towel. Now, by definition, tangent, so we've covered 2 trig functions so far. There's a total of 6 trig functions, but once you know sine and cosine, the rest you pretty much get for free. So our other 4 trig functions are written out right here. Okay, lots of scary symbols, but pretty simple definitions. So we'll take you through each one. The next most common trig function is called tangent. Tangent, by definition, is sine over cosine. That's why I told you that the 4 fundamental definitions you need in trig are pi, radian, sine, and cosine. All these other trig definitions are just derivations from sine and cosine. They're just doing different combinations of sine and cosine now. Tangent is going to be sine over cosine. Secant is going to be 1 over cosine. Cosecant is going to be 1 over sine. Cotangent is going to be 1 over tangent, or cosine over sine is another way you could have thought about it. Okay?
Yeah.
But let's take them one at a time. So tangent of theta, by definition, is sine of theta over cosine of theta. That's its definition. You ready? Now, sine of theta, if we do this substitution, and cosine theta, we're going to do this substitution. We're going to see what tangent of theta gives us with respect to this triangle. So tangent of theta, by definition, is what?
Cosine over sine.
Is sine of theta over cosine of theta.
Yep.
Now, with respect to this triangle, what is sine of theta?
An angle.
Y over.
It's y over r.
Or y over r.
That's what sine gives us. It gives us a ratio of y to r. Okay, so this is equal to y over r all over, what's cosine?
X over r.
X over.
X over r. And when you divide one fraction by another fraction, you just multiply by the reciprocal. So in other words, this is equal to y over r times r over x. Dividing by x over r is the same thing as timesing by r over x. dividing by 2 is the same thing as multiplying by 1/2.
Yeah.
Okay, and then what do we notice?
There's the top.
The r's cancel out. The r with the top cancels with the r at the bottom, and what are we left with?
Y over X.
Y over x. So, tangent just gives us y over x. Now look at this triangle. We have a name for y over x. What is that?
Base times height.
What would you tell a child y over x gives you? X is how far over we go. Y is how far up we go. So it gives us how far up over how far over. It gives us rise over run, which is the slope. The tangent of theta gives you the slope of that. So, without even thinking about it, what's the tangent of 0 degrees?
0.
0. Has no slope. Now, let's actually calculate that. We know that tangent of 0 is equal to sine of 0 over cosine of 0. What is sine of 0? What is the y coordinate at 0 degrees?
0.
0. What is cosine at 0 degrees? 1.
Yep.
Right? At 0, our x coordinate is 1, our y coordinate is 0. 0 divided by 1?
0.
0. Okay, let's do another one. Oh, we can't do that one yet. We're going to say 45 degrees. But already you can guess. What's the tangent of 45 degrees going to be? What's the slope at 45 degrees? 1. What's the slope at, what is that one going to be? 225 degrees going to be?
Negative 1.
Negative 1.
Negative 1. No, it's still 1. Negative 1 is this one. Tricked you.
Oh, yeah.
This line has the same slope as this line.
Yeah,
Yeah.
I knew that.
So then, over here at 135 degrees, we're going to get a slope at negative 1, and we'll plug that into our tangent function, and you'll see that. So tangent gives you slope. Good? Okay. Let's move on. Secant is equal to, is by definition 1 over cosine. Right?
Yeah.
So secant, by definition, is equal to 1 over cosine. But what is cosine?
Cosine is x over r.
X over r. So this is 1 over x over r, which is the same thing as its reciprocal, r over x. So secant gives you
0.
r over x. Oh, not at a particular point, just in general. What does cosecant give you? Cosecant, by definition, is 1 over sine. And sine is y over r.
So it's R over Y.
So it's r over y. It's just a reciprocal. Secant is just a reciprocal of cosine. Cosecant is just a reciprocal of sine. And then finally, cotangent is 1 over tangent, or in other words, it's a reciprocal of tangent. So it's x over y. So why do we have these 6 trig functions? Because they capture the 6 possible ratios you can create using 3 sides of a triangle. And depending on which 2 sides you care about, tells you which trigonometric function encodes it.
Yeah.
So that's why there's 6. That's why we care about the 6. In general, we never have to use any of these other ones. We could just use sine and cosine. These are just convenience trig functions. So we don't have to always just use sine and cosine. But we could get away with just sine and cosine.
That's only because you manipulate it. I'm trying to
Yeah.
make it easy.
It's just easier for us. I don't want to think about tangent of theta as sine over cosine. I want to think about it as a slope. That's a useful connection to make in your head. As an example. Okay. So we did those. We talked about scaling up. Now we're ready for our unit circle. So this is exactly what will be on your test next week. You'll be given a big blank unit circle that you will fill out. I sent those prints to the office. We'll do some practice ones. I'll get you some practice ones before the end of today here. But, so here's our unit circle. This is a circle with radius 1. I've labeled some points for you. Oops, one of my points got erased. This is a point, -1, comma, 0. Right?
Yeah.
We're going to populate all the coordinates of this point, of this circle. That's one thing that you're going to be required to do. The other thing you're going to be required to do is write out what the angle is on each of these in radians. So let's start with this. So really quick, we're going to go and we're going to talk about all the angles, and then we'll come and populate the coordinates. So first talk about angles. So I'm intending this right here to be 30 degrees. What is that in radians?
You're pretending that to be.
Yeah, we're saying that this green one is 30 degrees. Let's pretend I actually drew that correctly. That's what I was trying to draw. What is that in radians? 30 degrees is what portion of the circle?
112.
1/12. What's 1/12 of 2 pi? Or in other words, what's 2 pi over 12?
1/6.
Pi 6. So this is the same thing as pi 6. All right, this next one, I was trying to draw 45 degrees. It's 1/8 of the circle. And so, what's 2 pi over 8?
1/4, so pi 4.
1 pi 4.
So with that, following the pattern, that would be pi 2.
So following the pattern, what would this be? This is 60 degrees. 60 degrees is 2 30 degrees put together.
Yeah,
So what's pi 6 plus pi 6?
pi 12.
Pi thirds. If I give you 2/6 of a pizza, I gave you 1/3 the
Yeah.
pizza. So this is pi thirds. A 6 plus a 6 is a third. This angle straight up is 90 degrees. In terms of radians, it's pi halves. Good.
Makes sense.
Next.
What angle is that?
Pi 4/3.
Oh, sorry, yeah, I'll write the angle. So 120 degrees, or what?
Pi 2/3.
2 pi thirds. Good. This one, which is meant to be 135 degrees,
Pi 3/4.
3 pi fourths. Let me write that more angles so we can fit it. 135 degrees, or 3 pi fourths. All right, what would this angle be? Let's have you guys also do the degrees now.
160. Or-
What am I counting by? The green's counting by 30 degrees, and the red's counting by 45 degrees.
150.
Is this 150?
By 160. What?
Wait, what is green counting by?
It's counting by 30.
It's counting by 30 degrees. 30, 60, 90, 120,
Yeah,
150.
150. So this is 150 degrees.
I can't count.
Or in other words, it's, in terms of radians now,
Pi 4/3. Wait, no. Pi.
No, we did-
can't be more than 1, because
Yeah.
pi gets us here.
Right.
We're a sixth away from 1.
Pi.
So pi 6. Pi.
A sixth of pi away from 1 is what I meant to say. But yeah,
Well,
let you keep thinking about it.
Wait.
5 pi over
wouldn't
6.
it be
5 pi 6.
What's that? Oh, basically what's that?
5 pi 6. 1 pi 6, 2 pi 6, 3 pi 6, 4 pi 6, 5 pi 6. Now this one right here is
Pi.
Pi.
180 degrees, or 6 pi 6, or in other words, pi. Right?
Yep.
Next one, what's this angle?
7/6. Oh, sorry.
In degrees?
In degrees?
210.
210 degrees, or in other words, sorry,
7 pi 6.
7 pi 6. All right, what's this one? Counting by 45s.
4/3. Wait, no.
Add 45 to that.
195.
195?
Oh, I'm tripping. I saw 150.
Oh, that's a 180. Plus 45 is
225.
225. All right, we're in trouble, guys.
I know.
225 degrees, or in radians, is 45 degrees is pi fourths. We're adding a pi fourths to a pi.
5 fourths.
So pi.
5 fourths.
5 pi fourths. So this one's 5 pi fourths. All right. This next one, what is it in degrees?
It's 240.
It's what?
240.
240. And what is it in radians?
8. Wait, no.
It's 2 pi.
Oh,
4
2.
4/3
4/3. Pi.
4 pi thirds. Good. All right, this one,
Oh,
what's the angle?
it's 270.
270. What is it in terms of radians?
pi over 2.
3 pi halves. Right? 1 pi half, 2 pi halves, 3 pi halves.
Yep.
Yeah.
Okay, this angle right here,
That's
300.
300 degrees. In terms of radians,
That'd be
That's 4 pi thirds.
4 pi thirds, it's that.
Oh,
No.
my bad.
Nine. Oh, it's 3.
5 pi third over
5 pi thirds.
I gotta get the angles.
5 pi thirds. How could we have done that? 1 pi third, 2 pi thirds, 3 pi thirds, 4 pi thirds, 5 pi thirds, 6 pi thirds. If you want to think about
really
that.
8 pi.
Okay, what's this one? In terms of degrees?
that it's 315.
315 degrees?
Yep.
Or in terms of pi?
With that
7 pi over.
7 pi fourths. 7 pi fourths. All right. Our second to last one. What's that in degrees?
330.
330 degrees. Good. Or in terms of radians, it's
What's the last?
we got 2 pi. Oh, take away a sixth.
5.
But we got 12 pi 6 minus 1.
11 pi 6.
11 pi 6. 11 pi 6.
Oof.
12 6 gives us the whole circle, so take away one of those. All right, you see how painful that process was.
Yeah.
Okay, this is why I'm giving you your unit circle as the first test. We have got to get to the point where this is just automatic. And unfortunately, there is no special trick. You just got to get comfortable with it. You got to force yourself to do it a bunch of times. It's the same way that I cannot have you struggling. If I'm going to teach you an algebra class, you cannot be struggling every time you're looking at 6 times 5 and going, all right, let's see, 1, 2, 3, 4, 5, okay, 6, 7, 8, 9, 10, okay. Right? I know you know how to do it. That's not the point. The point isn't that you know how to do it. You got to be able to do it quick. So you're going to get your unit circle test next week. It's going to be timed. You got to do it fast.
What's the time limit?
Until I think you should have been done.
Okay.
I'll race you. I'll fill one out myself. Once I'm done, we'll see how much you've done. Okay, so those are the angles. Now let's do the coordinates. So we've already got coordinates in here that are obvious ones. So now we'll plug in more interesting coordinates. Let's start with this red one here, which is at 45 degrees.
Okay.
Okay? So here's our one for 45 degrees.
It's gonna be sine of 45.
Well, we want to figure out what sine of 45 is and what cosine of 45 is. So we're going to use geometry to prove what these things are. So I'm going to draw out this triangle. This is meant to be this triangle if you drop a vertical down right here, or an altitude down right here. So this triangle with angle 45 degrees, I'm trying to redraw that right here. You with me?
Okay.
Yep.
So what does this angle right here have to be?
90.
90.
A right angle, perfect. What is the hypotenuse of this triangle?
1.
1. Why is it 1?
Because that's all it's. That's
Because it's a unit circle. Perfect. We pull off the unit circle. Now I'm going to call this here x and this here y. Good so far? Now I know that this angle right here is what?
45.
45 degrees. What does this angle up here have to be?
45.
45. Because why?
Because
It equals
the
180.
angles has-
Right, the sum of the angles has to be 180. Okay, so the base angles are the same. So what kind of triangle is this?
It's right.
It's a right triangle. Good job. But that has nothing to do with these angles.
Is it isosceles?
Isosceles. Isosceles triangles. What the special property an isosceles triangle has?
Both x and y are equal.
X and y are equal. So whatever this distance is the same.
Okay.
So I'm going to relabel that as x because y and x have to be the same value in this case.
Okay.
You with me so far?
Yes.
All right. Now we're going to use our handy dandy Pythagorean theorem. Using that, what do I know?
X squared plus x squared equals
2x squared equals 1.
X squared plus x squared equals 1 squared.
Which is 1.
Which is 1, but just blindly plugging it in so far.
Yep.
One equation, one unknown. We can solve for x now.
So it's 2x squared equals 1.
So we have 2x squared is equal to 1. Divide both sides by 2. We get x squared is equal to 1/2. Take the square root of both.
Take the square out for x equals 1.
So yeah, take the square root of both sides. And so we get x is equal to plus or minus the square root of 1/2.
But it can't really be minus.
We know from our picture that it can't be minus. Minus would be if we flipped our triangle down here.
Yeah.
Yeah.
So we know that in our special case, we only care about the positive case. Okay? So let me write it over here more. X is equal to the square root of 1/2. You may remember from your radicals that the square root of a fraction is the same thing as the fraction of the square roots. So this is the square root of 1 over the square root of 2.
Oh, yeah.
What is the square root of 1?
1.
1.
So it's 1 over square root of 2.
1 over the square root of 2. Now, as a matter of convention, we don't like radicals in a denominator. This is a perfectly valid answer. But as a matter of convention, we don't like radicals in a denominator. What number can I multiply this by without changing it?
Square root
It's
of 2 over
reciprocal.
square root of 2.
There's
So
a
square
1.
root 2.
What's 1 times anything? What's 1 times
It's
x?
itself.
X.
X. So if I multiply by 1, I don't change the value.
So it's square root of 2 over
So
1.
I can multiply this by any 1 I want, as long as I don't change the value. So I'm going to multiply it by a very special one. I spell 1 funny.
That's cheating.
I multiplied it by 1. I took this number and I multiplied it by 1. So I did not change the value of the number. Now, what is square root of 2 times square root of 2?
2.
2. That's the definition of square root of 2. What's the square root of 2? It's a number such that when you multiply it by itself, you get 2. So this is equal to square root of 2 over 2. You with me? And that's the way you'll say it. If you got some kid fresh out of trig and you said, what's the cosine of pi fourths? They say root 2 over 2. So we just really found out that the x coordinate here is the square root of 2 over 2.
And we know that x and y are the same.
And we know, in this particular case, that y is also the same thing. So it is also square root of 2 over 2, root 2 over 2. So, question, what is the sign of pi fourths?
Root 2 over 2.
Root 2 over 2. That's what we just figured out. What is the y coordinate at pi fourths, at 45 degrees? Root 2 over 2, which is roughly 0.7 whatever it is. Okay, so that's one. Now we got to figure out some of these other points. Actually, before we do that, let's make an observation. Imagine now I took this triangle and I flipped it across the y-axis.
Okay.
That triangle would perfectly land right here. Picture's live.
Okay.
Get out of the way, Pi. We need to do a line. So if I were to perfectly flip that triangle over, it would perfectly land right here.
Yep.
And that coordinate would perfectly land on that coordinate.
Yes.
In other words, this coordinate is the same high up as that coordinate. So what's the y coordinate at this point?
That would just be flipped to negative.
It would be root 2 over 2, would be the height.
Yeah.
However, how far from the origin is it in the x direction?
The negative root 2.
The negative of it. Good, you see it. Sorry. Negative root 2 over 2. That is a terrible negative. Negative root 2 over 2. Okay. Similarly, if we were to flip this thing down, that would give us this point. And what would its coordinates be?
Negative root 2 over 2.
Negative root 2 over 2, negative root 2 over 2. Both negative.
Yep.
Perfect. And then finally, flip the triangle one more time. Now we're over here.
Root 2 over 2 and then negative root 2 over 2.
And root 2 over 2. And then negative root 2 over 2. Okay, so now we got all those points populated. And it turns out we only have to do one more triangle and then we're done. So the next triangle I'm going to pick is one of those green ones. I'm going to pick the green one that corresponds to 60 degrees. So we're looking at this triangle. With me?
Yep.
I'm going to redraw over here. Draw it in green to remind us it's our green triangle. So there's our green triangle. We know that this angle right here is
Pi over 3. It's
60 degrees. This angle right here is,
90.
and so this angle up here has to be,
70.
if I drew that a bit better, has to be 30 degrees. Okay, that's what we know about this triangle. What's the hypotenuse of the triangle?
1.
1.
1. How did you know that?
Yes.
It's on the
It's a unit circle.
It's on the unit circle. That's where we extracted this triangle from. Okay, what I'm going to do is I am going to reflect this triangle across this line. So, that does not look right. Let me do that. It should be a bit wider. Nah, still not good. Good enough though. Picture's lie, right?
Yeah.
What is this angle right here?
90.
90. And I've constructed it such that this is 60 degrees. And I've constructed it such that this then has to be 30 degrees. Okay, by construction. From geometry, we know how to do that construction. Okay. Question. What is this length right here?
So might as well 1.
1. What is the length of the bottom of the whole thing? Let's see if someone sees it.
2x.
It's 2x. Okay, so it's 2x. But what else is it? You should be able to determine the value now looking at this. Pictures lie.
1.
1! How'd you get 1?
Wait,
I
what?
just-
Oh, because it's all 180, they're all equal. 30 and 30 is.
Oh.
30 and 30 is 60. This is an equilateral triangle. 60, 60, 60. Pictures lie. So 2x equals 1. So what does x equal?
1/2.
1/2. So this goes over 1/2. We have our x coordinate here. What remains to be discovered is the height of this thing. You with me?
Yeah.
So I'm going to redraw this triangle down here now with the information we know plugged in. So this is 60 degrees. This is 30 degrees. Pictures lie. This is 1 and this is 1/2. We're looking for y. How could I get y now?
You can rearrange the Pythagorean theorem and figure it out.
We could use the Pythagorean theorem. I know that this side squared plus this side squared equals this side squared.
Oh, yeah.
So I know that
1/2 squared plus y squared equals 1.
maybe we don't really need this picture. So looking up here, I now know that this piece is 1/2.
Yeah.
Okay, so using the Pythagorean theorem on that triangle, and here's our y. Using the Pythagorean theorem on this triangle, I know that 1/2 squared plus y squared is equal to 1 squared.
Yep.
What is 1/2 times 1/2? 1/4. 1/2 of a half is a fourth. So I have 1/4 plus y squared is equal to 1, which is the same thing as what? Subtract 1/4 from both sides,
Y squared.
and I get y squared is equal to 3/4. Good. Now take the square root of both sides, and I get y is equal to plus or minus the square root of 3/4.
But it's just
In our special case, we know our y is going to be positive, so we're going to ignore the negative radical. So it's just going to be the square root of 3/4. Now the radical of a fraction is the same thing as a fraction of the radicals. So this is root 3 over root 4.
Yep.
And what is the square root of 4?
2.
2. So this is root 3 over 2. And that's as pretty as we're going to get it. So this is root 3 over 2. Root 3 over 2. Okay. Now, looking at our initial triangle, I'm going to take this thing, I'm going to tip it on its side. Actually, notice that this blue triangle is the same as the green triangle, right?
Yep.
So I'm going to take the blue one and tip it on its side like that. So I take the blue one and I tip it on its side.
Which side?
Oh.
Like that.
So that this is now 30 degrees.
Okay.
This is 60 degrees. The hypotenuse is still 1, right? How high up does the blue triangle go now?
It goes.
1/2.
It goes up 1/2. And how far over does it go?
Root of 3 over 2.
Root 3 over 2. Root 3 over 2. Notice that this is a triangle that corresponds to this point.
Yep.
So what is the x coordinate of this point?
Wait.
Root 3 over 2.
It's.
Root 3 over 2.
Yeah, that's right.
Okay, you see it? And then what's the height?
1/2.
1/2.
So all of those lines were just all corresponding to the same triangle anyway.
all the green lines, if you drop a vertical down from them, give you congruent triangles.
Yeah.
And all the red, same thing. And now finally, we can do our same trick of reflecting over and reflecting down and reflecting over. Make sense? All right, so great. Tell me the coordinates for this point.
Negative 1/2, comma.
Minus 1/2
Comma.
So root 3 over 2.
root 3 over 2. This point,
Negative root 3 over 2
and 1/2.
negative root 3 over 2 and 1/2. This point,
Negative root 3 over 2, negative 1/2.
negative root 3 over 2
Wait.
and minus 1/2. You're correct.
Okay.
Third quadrant, both negative.
Negative 1/2 and negative root 3 over 2.
Minus 1/2 minus root 3 over 2. Over here,
1/2 minus root 3 over 2.
and then finally this point,
The
Root 3 over 2.
root 3 over 2
minus 1/2.
and then
root 3 over 2 and minus 1/2.
Yep.
There you go, that's your unit circle.
Cool.
Let's see, we have 1, 2, 3, 4 points in each quadrant. For each point, we care about 4 sets of numbers, that's 16. Multiplied by 4 for each quadrant, 64. So 64 numbers that you need to plug in. Okay?
3 coordinates. Yeah.
Not bad. Okay, so,
Do you have to do that same triangle method for every angle that you have that you want to find the coordinates for?
for other angles, there's not going to be some nice geometric trick we can use. One of them we quickly noticed gave us an isosceles triangle. The other one we noticed reflecting it over gave us an equilateral triangle. You would have to find some special trick corresponding to each angle, which is a huge pain. In practice, how do we actually do these things? Comes from Calc 2. And there's a way of expressing cosine as an infinite sum. And so you can just calculate that sum to however many decimal places you care about. The sum is such a way that it decreases, the numbers you're adding together decrease in value. So you're guaranteed to get the first 5 digits if you add up the first 8 terms or whatever. So in practice, that's what you do. And if you were writing a calculator to calculate these things, you'd be using that Calc 2 concept. You would not be coming up with some geometric construction.
But in general, like on the test, if you want
On the test, these are the only angles I will give you. You see them all. Anytime I give you an angle, it will be one of those.
Okay.
Most likely.
Mostly.
I can still do some clever things, and we'll get to those when we get to them. We can look at sums and differences of these things to figure out how to calculate those.
Okay.
That'll be after we talk about trig identities, though, which we won't be talking about today. So, nothing to worry about for a second. Any other questions with this stuff before we move on to the next board? All right, and then forever hold your peace.
You guys saw the triangle?
Oh, thank you. I almost missed part of it. This is going to be the type of thing on your homework. Okay, actually applying all this stuff now to triangles. Here's something that you might be given. You're gonna be on your homework given something like this. And this is gonna say solve the triangle. That means find the variables.
Yeah.
So how do I figure out what x equals?
It's
Using
cosine of
Pythagorean.
theta.
Cosine of theta if it's on a unit circle. In general, always and forever, how do we calculate x?
Hypotenuse.
R times cosine of theta.
That makes sense.
So in this example, right, x isn't just a cosine of pi 6. That's what would be on the unit circle. We do cosine of pi 6 and multiply it by 8 because we're stretching this triangle out
Right.
so that the hypotenuse is 8. So it's going to be 8 times cosine of pi 6.
Okay.
And what is cosine of pi 6?
30 degrees, right?
30 degrees is pi 6. So what's the cosine at pi 6?
Cosine is root 3 over 2.
Yeah.
Root 3 over 2. The 2 will cancel out with the 8, leaving me 4, so it's just 4 squared to 3. And there we go. You just figured out how long that side is. Next question is, how tall is it? The y is equal to what?
8 times sine.
8 times sine of our angle, which is pi 6.
Pi 6.
What is the sine of pi 6? 1/2. So it's 8 times 1/2, or in other words,
4.
4. So that triangle has exactly a height of 4.
And the length of 4 times root 3. 4 root 3.
Sorry, what? And a length of 4 squared to 3. Yes. So you just figured out the length of that triangle and the height. So your homework, I'm going to give you a bunch of examples that are solve the triangle. And you're going to do that a bunch of times.
Are the angles going to be always on a unit circle?
Yes.
If the angle is not, no, sorry. So for the homework I gave you, you're going to have to use a calculator. So I'll give you one that's going to be on your homework. You might see something like this. And we'll do some homework problems at the end of class just to help you get comfortable with it.
Okay.
But we'll probably say something like 57 degrees here. And it will say like 10 here, and then x and y. In this case, x is just equal to 10 times the cosine of 57 degrees. You'll plug that into your calculator,
And then it would just calculate the length.
and it will come out to whatever it will come out to. In this case, it will probably be close to like 15, but whatever. Not 15, 7.5. And then half of that.
Okay.
Okay? And then similar thing for the y. Or it might give you the x in the angle, and you'll have to figure out these other ones using all your trig functions.
But we're not allowed to use a calculator on the test.
On the test, you won't be able to use a calculator. On your test, I will stick to angles that you already know and love. You're going to like that I do that on the test, because it's annoying having to work with these numbers that have like 6 decimal places, and you're wondering how many decimal places should I keep track of.
Yeah, okay. That's fair.
Okay. Now, we covered that. Moving on to the next board. Let's get that out of the way. Good enough. Seems like I see it all. Don't let me go past this squiggly line without moving the camera. So that will most likely happen a couple times this year. Okay, so there's our trig review. Now we're going to quickly talk about sets. What is a set? We can't give a precise definition, but intuition. A set is an unordered, unique collection. Collection of what? Doesn't matter. Of stuff, of things, of thems, whatever it is. Now, what does this mean by unordered and unique? First off, when we start writing a set, we start with one of these brackets. Then you list out the elements in your set. In this case, I list out 1, 2, 3, comma separated. Then you do another bracket that signifies that your set is over. This is a set. It is containing the objects 1, 2, and 3. Here's another set. It is containing the objects 3, 2, and 1.
Same set.
What we mean by a set being unordered is that order doesn't matter. So this set and this set are the same set. They are the set containing the objects 1, 2, and 3.
Oh, yeah.
This is a set containing 1, 1, 2, 3, 3, 1. But when we say unique, we mean duplicates don't matter. So this is a set containing 1, 2, and 3. Question, how many things are in this set? 3. There's only 3 things in that set. Because that set is equal to that set only has 3 things.
Yep.
So sets, it's these collections where order doesn't matter and duplicates don't matter. It's that simple. Good so far? Okay. Common sets with these fancy symbols. These fancy symbols, I can't help but use them a lot, so you gotta get comfortable with them. First one, the 0 with a line through it is called the empty set. That is this set. It's just really annoying writing those. And so we have this symbol for the empty set. Good so far?
What's the point of those?
The empty set?
Yeah.
It's super valuable.
For one, if we were doing a completely rigorous development of the real numbers, this would be our definition of 0.
Oh.
Everything in mathematics we can reduce to set theory. Set theory is presupposed in every field of mathematics.
Yeah.
And everything ultimately has a set theoretical definition. Technically, every mathematical object you're talking about can be defined in terms of sets. Sets aside, sets aside, sets aside, sets, and that's all it is.
Yeah.
So sets are very useful. But we won't think about sets that way. So we will not think about that as 0. We will just think about that as the empty set. Okay, so that's the empty set. That's this one. This is a set of natural numbers. What are the natural numbers?
1, 2, 3.
0, 1, 2, 3, 4, etc.
Do you count 0 as a natural number?
Some authors are incredibly rude human beings who decide not to include 0 as a natural number, which is the most unnatural thing to do, especially if you're going to be doing a set theoretical development of the natural numbers, because you want to include the empty set, which is 0. So we already have a great symbol for just the positive integers, and so we don't need some other special symbol. So all you mathematicians out there watching this, since you all do, change your ways. Use NRAM. Okay. Z here stands for integers, right?
Yeah.
Why? I don't really know. Not sure the history on that. So this is -2, -1, 0, 1, 2, 3, ... Going on forever. Infinite set. Those are both infinite sets. If I were to write a Z here, and I put a plus up there, that means we only care about the positive integers. And there you go. There's all your numbers, 1, 2, 3, 4, 5. And we have a symbol for it.
Yeah, wouldn't that just be natural?
That would be the naturals without 0. So here's how you signify the naturals without 0, and let that signify the naturals with 0.
Okay.
And that way we have the notation we want. Furthermore, I could have done Z with the negative sign up there. That means just all the negative integers.
Yeah.
Okay, so those are those two. Next, we have the rationals. The rationals are the set of all the fractions of integers we can make.
Yep.
So this has all sorts of things in there. There's -1/2. There's 17 over 91. There's 2,107 over -3, etc. Any possible fraction of integers you can make is in there, with the exception of you can't have 0 in the denominator.
Yep.
Those are the rationals. What are the reals? How many of you know what? Let's not say it that way. The reals are pretty much what you think of when you think of a number. Any number you can think of, chances are you're thinking of a real number. Give you an example of something that's a real number but not a rational is the square root of 2. Square root of 2, that's a number. It's not a rational number. You can't express that as an integer over an integer. Another example, pi. So pretty much anything you think of when you say a number, chances are you're thinking of a real number. If you know what the complex numbers are, well, then you should already know the real numbers, and so you should know the exceptions.
Okay.
So those are our common symbols and our common sets that we'll talk about. Any questions about any of those? You'll get used to them as I use them a lot. Okay, now we're going to introduce what we call set builder notation. This is a way that we write out a set. This is particularly useful when we're trying to write out infinite sets. Sets have infinitely many elements in them. I can't write out all infinitely many of them, so I need to somehow give you a rule for how you generate the set so you get a sense for what it is, instead of just relying on me giving you some sort of pattern. So, set builder notation, how does this work? We write some dummy variable, typically like an x or an n or a y, something like that, colon, and then some condition that your dummy variable satisfies. For those of you comfortable with logic, some predicate in terms of your dummy variable. If your condition evaluates to true, we take that instance of the variable. If your condition evaluates to false, we don't. So let's do some examples, because that was a lot of words. One way we might represent the evens. What are the even numbers?
They're numbers that can evenly be divided by 2.
So it's the set of all n. Here's my dummy variable, n, arbitrarily chosen. The colon we typically read as such that. It's all the n such that, sorry I didn't introduce that symbol yet. N is an integer, that just means is in. N is in the integer, so it's an integer. And n is divisible by 2. That vertical line means is divisible by. That's what it means to be even. So what are your evens? They're all your n's, where n is an integer and n is divisible by 2. That's what it means to be even. And so now I can represent an infinite set because there's an infinite number of evens. And you don't have to guess at some pattern. Let's try and reverse engineer one of these now. Here I gave you something and you have to guess at some pattern. Right? How could I have rewritten this in set builder notation?
That's just x squared. So it would be
So it's just the set of all perfect squares, right? 0 squared, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, etc.
So it's x in.
It's a set of all x such that
X is in the integers.
x is an integer.
And x. How do you say that? How do you represent a perfect square? And the square and.
X squared.
Fair enough.
It's X.
And x squared.
What do you do? It can be
And
square
next squared
rooted.
what? It's got to be a condition. And it can be square rooted. We can say and, here's a symbol for and the square root of x is an integer. That works.
That works.
Square root of X. Yeah, that would do.
Only perfect squares have their square root being an integer.
Yeah, that would work.
Yep.
That's one way to write it, perfectly valid way to write it. I'm going to write it a bit nicer way. At least I think it's nicer. It's going to be a set of all y such that y is equal to x squared, where x is an integer.
Oh, that's what I was thinking. Okay.
Another perfectly valid way to write it. Nothing wrong with this. This is just a bit simpler to read. And comma just means the same thing as and. You can say and this, and this, and this are just comma. And comma separating means you have to satisfy all the conditions.
So, are you going to be asking us to write these in homework and in test, I'm assuming?
No.
No?
No, this is just laying some foundations. Okay. So that's set builder notation. Now, let's talk about some common relations on sets. A relation is something that you can call true or false. So in math, we often talk about two types of things. We talk about operations and relations. Look at 2 is less than 6. what is that?
It's a relation to 6.
It's a relation, so what, is this false or true?
True.
2 is less than 6 is true. This is something that's true. Now look at this. 2 plus 6, what's that?
That's
8. Relations take terms and spit out true or false. Operations take terms and spit out terms. So we're going to look at relations on sets, things that you can call true or false, and then we're going to look at set operations, which take sets and spit out sets. Make sense? So first let's talk about some common relations on sets. The first one is saying that x is in some set A. That's right, as x is in A, or x is a member of A, or x is an element of A. All the same thing. Let's see some examples. Tell me if I lied to you. 1 is in the set 1, 2, 3.
True.
True. The set containing 1 is in the set containing the set containing 1, the set containing 2, the set containing 3.
True.
True. This is one of the elements in that set. It's right there.
Yep.
Alright. Is the set containing 1 inside the set containing 1, 2, 3?
No.
No.
No. This is not an element in any of those. Is the set, or is 1 a member of the set containing 1, the set containing 2, the set containing 3?
No.
No. So it's not a member. So you do that line through it just means not a member. Is a member, is not a member. So all these evaluated to true. Good?
Oh, yeah.
Okay. Next relation. Subset. A is a subset of B, where those are both sets. What does it mean for A to be a subset of B? It means if X is in A, then X is in B. Anytime X is in A, X is also in B. That's what it means for A to be a subset of B. So, the set containing 1 is a subset of the set containing 1 and 2 and 3. Because everything that's in this set is in this set.
That's, yeah.
What's in this set?
1.
1. What's in this set?
1.
1, 2, and 3.
Okay.
So everything that's in here is in here. Let's look at this really quick. Is this set a subset of this set?
Yes.
Is this true?
Yep.
This is a subset of this. Forget this for a second.
Yes.
Yes.
Yes. Everything that's in here is in there. Let's see. 1. Yep. 1. Yep. 2. Yep. 3. Yep. 3. Yep. 1. Yep. Everything that's in here is also in here. So this is a subset of this. Is this a subset of this?
Yes.
Yes.
No. Oh, yes.
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 They're both subsets of each other.
So they're the same set.
We'll find out that that's our definition for sets being equal when we extend our definition. of equality. So, subset. So the set containing 1 is a subset of the set containing 1 and 2 and 3. The set containing 1 and the set containing 2 is a subset of the set containing the set containing 1 and the set containing 2.
Yes.
Everything that's in here is also in here. 1 is not a subset of the set containing 1, 2, and 3. And we'll go so far as to say 1's not even a set. So obviously it's not a subset.
Yeah.
That's true.
Okay. The set containing 1 and the set containing 1 and 2 is not a subset of the set containing 1 and the set containing 2.
Yes.
Everything that's in here is not in here. 1's in here, 1 is not in here. Neither of those elements are 1. That's the set containing 1. It's a very different object from 1. Okay. Question. Is A a subset of A? Given that A is a set, is A a subset of A?
Yes.
Yes.
Yes, every set is a subset of itself. Everything in A is in A. So we're good. A is a subset of A. Question. Is A a subset of the empty set?
No.
No.
Is everything in A in the empty set?
No.
No, not unless A happens to be the empty set. Outside of that, no. So in general, this is not true. Is the empty set a subset of A?
Yes.
Yes.
Every time.
Everything in the empty set is in A. Watch, I'll check for you. Want to see me check for you again?
One more time.
We checked everything in there. What's everything in there?
Nothing.
Nothing. So everything in there is always in there. Okay. Next relation, set equality. What does it mean for A to equal B? It means A is a subset of B and B is a subset of A. If they're subsets of each other, they're equal. How do I know two sets are equal? How do I know A is equal to B? Everything that's in A is in B and everything that's in B is in A.
Yep.
That's how we knew all these sets were equal. Everything in one is in the other and everything in the other is in the one.
Yep.
Okay? Now we have proper subset. So sometimes we think about subset as kind of like less than or equal to. We kind of think about that as like the less than or equal to sign. And we sometimes think about proper subset as kind of like the less than sign. So less than or equal to means that they can be equal. If A is a subset of B, A can be equal to B, which is why we include that little line down there. A is a proper subset of B means that A is a subset of B and not equal to B. It's kind of like X is less than Y means X is less than Y but cannot be equal to Y. So the line, if it has that line underneath, that line usually means we're allowing them to also be equal. This one does not have that line underneath. We are not allowing them to be equal. So A is a proper subset of B, meaning A is a subset of B and A is not equal to B. So the set containing 1, 2, and 3 is a proper subset of the set containing 1, 2, 3, and 4. If I were to get rid of 4, is this true?
Yeah. No.
No, because now they're equal. But as long as I make sure they're not equal, now we're good again, right?
That's not a subset.
No, because now this isn't even a subset of that. Because we don't have everything in here showing up in there. So it's not a subset, so it's not a proper subset. Okay. Question. Can we ever have A is a proper subset of A?
No.
No, because it's equal to it. Is the empty set a proper subset of A?
Because what if A is the empty set?
Oh, yeah, A's always.
As long as A has at least one element in it,
Then yes.
then we're good. Outside of that, if A is the empty set, then it doesn't work anymore.
Yeah.
Okay?
Okay.
So we talked about our 4 basic relations on sets. Is a member of, is in, equals, subset, proper subset. Not bad? Okay, so now let's talk about set operations. These are not things that we call true or false. They take sets and spit out sets. They're operations, not relations. Okay, so we're going to go over intersection, union, set difference, and then set cross product. Okay, so starting with intersection. A intersect B, by definition, when you do the colons equals, that means we're defining something new. So it's saying this is equal to this, and we're defining it right now to be equal to this. It's the first time we're introducing the symbol. So when you see me do the colon equals, that's what that means. Okay, so A intersect B is by definition the set of all x where x is in A and x is in B.
Yep.
A intersect B is a set of everything that is in both A and B. Let's jump down to our example here. We're going to jump down to this example as we go over each operation. So let A be the set containing the numbers 1, 2, 3, and 4. Let B be the set containing the numbers 3, 4, and 5. What is A intersect B equal to?
The set containing 3, 4. 3 and 4.
The set containing 3 and 4. Because 3 and 4 are in this set, and 3 and 4 are in this set. And those are the only numbers that show up in both sets. Read that definition one more time. What's A intersect B? It's a set of all the things, all the x's, such that x is in A and x is in B. It's a set of everything that shows up in both. In terms of a picture, if this was A and this was B, A intersect B would be everything in their intersection. It would be everything right here if we drew it pictorially. Make sense? Okay. Moving on to our next one. Union. A union B, by definition, it is a set of all x such that x is in A or x is in B. In other words, it's the set of everything that shows up in at least one of the two sets. Maybe shows up in both, but it has to show up in at least one of the two sets. So not Caleb, what is A union B?
The
One.
second thing you have.
1, 2, 3, 4, and 5.
1, 2, 3, 4, 5.
So union means both combined.
Means a union together.
Yeah, I don't like saying the word combined. You've got the right intuition. Now just get the right word.
Union.
It's everything that shows up in either of the two sets.
Yeah.
So A union B is literally everything
In those sets, though. Just A and B.
in those sets. It does not include this point right there.
Makes sense.
Okay, next, A minus B. This is set subtraction. This is not integer subtraction or real number subtraction. So this is a set of all x where x is in A and x is not in B. So what is A minus B, Zach?
A minus B would be. It would be 1, 2, 3, and 4, subtract 3, 4, and 5.
Right, so everything in this set
Yeah.
that's not in this set. What's everything in this set that's
Oh.
not in this set?
It's 1, 2.
It's just 1 and 2. Perfect. All right, Alex, what's B minus A?
The set containing 5.
The set containing 5. Everyone see that? Pictorially speaking, A minus B, I'll do the lines this way, A minus B would be everything in this part of A. And B minus A would be everything in this part of B. Notice that A minus B is not the same thing as B minus A.
Yes.
Yes.
However, A union B, or A union B is the exact same thing as B union A.
Well, yeah.
And A intersect B is the exact same thing as B intersect A. The other way we say that is this is commutative, this is not. Swapping the term sides changes the term that comes out. Okay. And then we'll come back and talk about cross product in a second. We got to introduce you to the concept of lists. I'll move my camera. Any questions on any of this before I move my camera?
Nope.
All right. Okay. So now we're moving on to lists. Lists are very similar to sets, except order matters and duplicates matter. So the list, instead of using curly braces, we use parentheses to signify that's a list. So here's a list containing the numbers 1 and 2. The list containing 1 and 2 is not the same thing as the list containing 2 and 1. We often use two-element lists to talk about points. The point 1, 2 is not the same thing on the xy plane as the point 2, 1. Those are very different points. Similarly, they're not the same thing as 1, 1, 2. If we interpret that as a point, that's now a point in three-dimensional space. That's very different from a point in two-dimensional space. So duplicates matter and order matters. Good so far?
Yes.
And then very importantly, a list and a set are very different. A list is never equal to a set. Well, there's a set theoretical definition of a list, but setting that aside, for the purposes of this class, a list is never equal to a set. Okay. Now we have a special name for lists that only have two terms in it. We call them ordered pairs. So an ordered pair is a two-element list. If only two things show up in the list, it's an ordered pair. Question, is this an ordered pair?
Yes.
Yes. Question, is this an ordered pair?
Yep.
What do we have in here? We've got the set containing 1 and SpongeBob.
Yep. This is an order pair.
Ordered pair.
Two elements.
Okay. This one's Bob and Frank.
Yes.
Well, look, Bob has 3 letters. What does that matter? We comma separate the things in our list. Something, comma, something.
Right.
Just 2 things in there. Good? All right. That's an ordered pair. Now, a relation. A relation is a set of ordered pairs. So T here is equal to this set. Question, how many things are in that set?
4.
4 things in it. This thing, comma, this thing, comma, this thing, comma, this thing. Is everything in there an ordered pair?
Yes.
Then this is a relation. If I come on here and I do comma 2, is that a relation?
No.
No, because everything in there is not an ordered pair. A relation is just a special type of set. It's a set where everything in there happens to be an ordered pair. We like these relations very much. You can name them whatever you want. So I'm going to do this weird L, and I'm going to have it equal to this set. You with me?
Okay.
So it's 0, 1, 0, 2, 1, 2, 0, 3, 1, 3, 2, 3, 0, 4, 1, 4, 2, 4, 0, 5, 1, 5, 2, 5, 3, 5, 4, 5, etc. Following that pattern. You with me? Okay. We have some notation. When 2 things show up in a set, if I've got the ordered pair AB in a relation, not just a set, a special type of set called a relation. So if I know that some ordered pair AB is in my relation, we often write it like that. We write the name of the relation between them.
Makes sense.
So if this is R, 1, 2 is an ordered pair in R, so I could write 1 is related to 2 in this relation.
Yes.
Similarly, from here, let's pick 2 things in here. 0 and 3 are in there. So another way I could write that is like this.
Yep.
And so this is a definition of the less than relation on the natural numbers.
Yep.
What is the less than relation on the natural numbers? It's an infinite set of ordered pairs, where all the ordered pairs are where the left-hand element is less than the right-hand element. List it out. So this is just shorthand for saying this. I could have said 0, 3, epsilon. 0, 3 is in less than. That notation makes perfect sense. You've never seen that notation before. You've seen this 100 times. 0 is less than 3. They say the exact same thing. That symbol you've been seeing over and over again is a representation for an infinite set of ordered pairs. That's what it is.
Yep.
So, I'm giving you big boy definitions of all these things now, rather than just intuition. Actually understanding what precisely these things are. That's what it is. Okay. Now, we skip over one operation, cross product. So, A cross product B gives me the set of ordered pairs XY, all the ordered pairs XY, where X comes from A and Y comes from B. It's a set of all the possible ordered pairs you can make, where X comes from your first set, your left-hand element comes from your first set, and your right-hand element comes from your second set. Let's do a concrete example. I'm going to do the set containing 1, 2, crossed with A, B, C. This is equal to the set of all the possible ordered pairs I can make, where my first element comes from here and my second element comes from here.
Yes.
So tell me one thing in the set.
The ordered pair 1, comma A.
1 comma A. That's something in there because 1 is one of the things in here and A is one of the things in here.
Yes.
What's another ordered pair I can make?
The ordered pair of 1B.
It's 1B. What else?
2B, 2C.
2B. Oops. 2B. We'll come down here and continue it. Parenthesis 2C. What else?
2A.
2A.
1C.
1C. What else?
Is that it?
That's,
Is that it?
yeah, that's.
How can we quickly check if that's it? We have 2 options for the first element, 3 options for the second. What's 2 times 3?
6.
6. How many did we list out?
6.
We got them all. So that's cross product. A cross product between 2 sets always spits out a relation. It spits out a set, but it spits out a certain type of set, called a relation. Okay, now, remember, we have sets. A relation is a special type of set. Now we're going to talk about a function. A function is a special type of relation. Okay, so function. A relation F, so far what do we know about F?
It is a
It's
set
a
of relations.
relation.
It's a relation, it's a set of ordered pairs. A relation F is called a function now, provided that if A and B are an ordered pair in F, and A and C are an ordered pair in F, then B has to be equal to C. Let me use language that you're more comfortable with. If F maps A to B and F maps A to C, then B and C have to be the same thing. In other words, F has to map each A to one and only one thing.
Yes.
If 2 ordered pairs shows up in F, they better be mapping to the same thing.
Yes. Okay.
Make sense? Okay, question. Here's a relation. F, is it a function?
No.
No? Why not?
The ordered pair 2 and 4 and 2 and 5.
Because it has 2 4 in here and 2 5 in here.
Yeah.
Okay, let's replace that with a 1. We good now?
No.
No?
Got the 1, 2.
We replace it with a 5.
Yeah, that's fine.
But I have 5 goes to 5.
It's fine.
So what? Good response. Okay, more notation specific for functions. If A and B are an ordered pair in F, we write that as f of A equals B. The thing paired with A in F is B. The thing paired with A in F is B. The thing paired with A in F is B. Remember, your functions are always sets of ordered pairs. That's what they are. This is telling you what's paired with A. B's paired with A. That's what you're saying here.
Yes.
Okay. Now I'm going to write out some relation for you. A relation that happens to be a function. Here's a relation. 0 goes to 0. 1 goes to 1. 2 goes to 4. 1/2 goes to 1/4. Square root of 2 goes to 2. In other words, I'm pairing each thing with itself squared. I paired 0 with 0 times 0. I'm going to pair 1 with 1 times 1. I'm going to pair 2 with 2 times 2. I'm going to pair 1/2 with 1/2 times 1/2. I'm going to pair square root of 2 with square root of 2 times square root of 2. You see it? Now that's a stupid way to write this function. So let's use our set builder notation that we know and love. This time, since it's ordered pairs, my dummy variable has to be in terms of ordered pairs. So f is a set of all x comma y, such that y is equal to x squared.
Oh, okay.
Or another way I could have written that is f is a set of all x and the thing paired with x, such that the right-hand thing is equal to the left-hand thing squared. Both of these are perfectly fine.
Yeah.
Which is why now we're super lazy as mathematicians, and we say, oh, we kind of infer from context that this is what we're saying. If you just give me this piece, I kind of know that's what you're talking about. And if you just give me this piece, I kind of know what you're talking about. So you're used to being told about the function y equals x squared. What is the function y equals x squared? That is an infinite set of ordered pairs, of all the ordered pairs that satisfy that expression. So this is shorthand for an infinite set, this thing. This is shorthand for an infinite set, namely this thing. Make sense?
Yeah.
All right, any questions about those? Before we move on to the last word and just graphing these things? Okay, So finally, what does it mean to graph a function? What do you do when you graph a function?
You label all the possibilities.
You map.
You interpret all these ordered pairs as points in the xy plane and plot them. That's all you do. So to graph a function, we interpret each ordered pair as a point on the xy plane. That's all it's doing. So let's graph a function. We'll just graph the one that we already have out there. So we'll look at the function f of x is equal to x squared. This is shorthand for an infinite set.
Right.
What are some of the things I know are in that set?
0.
0 what?
Comma 0.
0, 0 is in there. What else is in there?
1, comma 1.
1 comma 1's in there. What else is in there?
2,
2 comma 4.
1 half, 1 fourth.
Negative 1 is going to show up as one of these left-hand elements, right?
Yep.
Negative 1.
Yeah, negative 1.
Negative
That's
1.
perfectly valid.
Negative 1, 1.
And what does it go to?
1.
1.
1.
Yeah.
Negative 2 is going to show up. What does it go to?
4.
4.
4. And we can't write everything in there. But if we take all these points, if we take all these ordered pairs, and we interpret them as points in the xy plane.
What does it mean to interpret them as points? Like, mathematically.
So this is a point.
Mm-hmm.
That's an ordered pair.
Yeah.
A point is a geometric object. An ordered pair is a list of elements.
But what's the connection?
What's the connection? We would say that the coordinates of that point are being symbolized by an ordered list.
Yeah.
So when you take your ordered pairs, you interpret them as coordinates of points and plot the corresponding points. That's what we mean by the graph of a function. So we take all those, we interpret them as coordinates of corresponding points, and we plot those points. Let's see, 2 went to 4, right? So 1 went to 1, 2 went up here to 4. Let's see, we have 0, 0 there, so start with that. We have negative 1, 1. We have negative 2, 4. And so we're plotting all these points. If we were to pick a bunch more points in there and plot them all out, then we notice that it gives us something looking like this, right?
Yeah.
Something we call a
Parabola.
parabola. And then we do something without really even thinking about it. We just make this nice smooth connection between all these points. As though it just continues that way. Without a clue if it actually does, right? For all we know, there's a bunch of squigglies between all the points that we plot.
What do you mean by that?
I mean, we assume, after you plot enough points, right? So you plot this point, this point, this point, this point, this point, this point, this point.
Yeah.
We just, for some reason, assume that there's just a nice smooth connection between all those points. How do I know that my function isn't doing this?
Why would it?
Why wouldn't it?
Why isn't it doing something squiggly? I guess this would cause it to not pass a vertical line test, but why isn't it this nice smooth transition?
Because that's
We'll justify that in calculus. You need calculus to justify it. But there's no reason that it has to be. You can only test a finite number of points, and yet we plot infinitely many with that ink there.
Oh, okay, yes.
We didn't test all those points. All right, we justify it thinking it just flows nice like that. We'll get to justification somewhere in calculus. Okay, finally now, again, go back to what we know it looks like, since someone with a tie once told us that's what it looks like, so we believe them. Right? Now, what are all the left-hand elements that show up in the sink?
Integers.
Well, in this case, we happen to choose integers, but I could have just as easily done 1/2 goes to 1/4.
Okay.
I could have done root 2 over 2 goes to what?
2 over 4. 1/2.
1/2. And I could have gone on my merry way.
They're all real numbers.
Do one more. Pi goes to pi squared. Pi squared, perfectly fine number.
You get the
It's, yeah,
So what are all our left-hand values that show up in there?
they're real numbers.
All the real numbers show up in there. R. That's what we mean by the domain of a function. It's just called the left-hand pieces. Similarly, what are all the right-hand things that show up in there?
real
Also
numbers.
real numbers. Also real numbers. Wait. Yeah, they're also real numbers.
make no negative 3 come out of this function?
Oh.
They're all
What can I
positive.
plug in to make negative 3 come out?
You're right. No real number can go in there that big.
How do you know there's nothing? Maybe if I go far enough this way, it shoots that down to negative 3.
No, because you can't have the square root of a negative number is not a positive number. Or the square root of any number will not be a negative number.
There's an easier way to say what you're trying to say. What's a positive times a positive?
Positive.
Positive. What's a negative times a negative?
Positive.
What's 0 times 0?
0.
0. So we can't take a number multiplied by itself and get a negative number.
Yeah.
Doesn't work.
You
Okay.
can't take a real number and do that.
Can't take a real number and do that. That's what number means in this class.
Okay.
We'll ignore complex until they come up. I'm not sure how soon the author introduces them. Okay. So all the numbers starting from 0 and going to infinity. We have interval notation for that. That looks like this. Have you seen interval notation before?
Yes.
Never? So there's a couple different ways we can write an interval. Let's just write a bunch of them. If I do the interval 1 to 2 now, and I'm talking about as an interval. This is not an ordered pair anymore. Unfortunately, we use some of the same notation over and over again. It's kind of ugly. 1 to 2, this means all the numbers x such that 1 is less than x and x is less than 2. Or in other words, it's all the numbers between 1 and 2.
Yeah.
So 1.5 is in there. 1.9 is in there. 1.999 is in there. Is 2 in there?
No.
No, because 2 is not less than 2.
Yeah.
In general, for any interval AB, by definition, it's a set of all x such that x is greater than a, and x is less than b. Make sense? Now, if I include a square bracket on one side, that means also including a. So now x has to be greater than or equal to a.
And you can do that both sides.
And you can do that both sides. If I were to put the square bracket here, that means
it can equal b2.
it can equal b2. Now finally, I might say everything from a onwards. This is a set of all x such that a is less than x. And there is no upper bound. So it goes off to infinity.
Yeah.
And if I would have made this a square bracket,
It can equal.
then we include a. If I were to make this a square bracket,
That doesn't work.
Yeah.
then we're broken, because you can't include infinity, because it's not a real number.
Right.
So that's not notation. So it's always rounded like that.
Alright, yeah.
And then similarly, you can have negative infinity to b. This is all the numbers less than b, or all the numbers less than or equal to b.
Yep.
Yeah.
And that's interval notation. Okay. That covers the foundational stuff that I wanted to do. So we'll start chapter 1 next week, going through the first couple sections. We'll make sure we get you your book. I don't think I'm forgetting anything else. Any questions? Okay. So I'll go get your printouts and we'll get started.